Today's video is going to cover curve sketching, except this time we're going to use the first derivative and second derivative number line to help us. Let's start with the domain. Again, domain is anything that doesn't make that denominator equal to 0. So actually, I don't think there's anything that does make that denominator equal to 0. So great, there are no restrictions to the domain, so our domain is negative infinity to positive infinity. That means no vertical asymptotes or holes because there are no restrictions, and those are both restrictions. All right, to find x-intercepts, we're going to make y or f of x equal to 0, which is essentially making the numerator of this equal to 0. That means x equals 0. So 0, 0 is my x-intercept, my only x-intercept, and it's also my y-intercept. End behavior is basically asking what is the limit of the function as x approaches positive infinity and as x approaches negative infinity. As we approach positive infinity, remember we care about terms of highest degree, so we'll use 2x cubed and x squared. Okay, the degree of the numerator is greater than the degree of the denominator. That means we're going to have a slant asymptote. One direction will go toward positive infinity, one direction will go toward negative infinity. 2x cubed over x squared reduces to be 2x. After direct substitution, quote, with infinity, then you have simply positive infinity. That means the limit as x approaches negative infinity, 2 times negative infinity is negative infinity. How do I write that as end behavior? F of x will approach negative infinity as x approaches negative infinity, and f of x will approach positive infinity as x approaches positive infinity. It's now time for us to use a first derivative number line to figure out our critical numbers, see if we have any relative extrema, max or min, and the intervals of increasing and decreasing. To find critical numbers, we look for where is the derivative equal to 0 or where is the derivative undefined. F prime is defined for all x's, right? There's nothing that would make this denominator equal to 0, so we're just going to find where it's equal to 0, and f prime is equal to 0 at, using zero product property, at x equals 0. And this will give you imaginary values. So the only critical number is at x equals 0. Let's create an f prime number line to determine if my intervals are positive or negative to the left and right of our critical number. So f prime of a number less than 0, I'll just figure out what is f prime of negative 1. Is that going to give me a positive value or a negative value? Looks like it's positive on top and on the bottom as well. So that's going to be a positive value. And then f prime of positive 1. Yeah, all of these x's are being squared, so, and then everything's being added. So yes, this is all positive. Both of these intervals are increasing. So is x equals 0, this critical number, does that give us a max or min, a relative extrema? No, it does not. So there are no relative extrema. Let's try making an f prime prime number line to determine intervals of concavity and if there are any points of inflection on this graph. Possible points of inflection occur when the second derivative is equal to 0. So let's go ahead and solve that. The second derivative is equal to 0 at 0 and at plus or minus root 3. All these x values are candidates for possible points of inflection, and we will check the intervals now. F prime prime of negative 2, positive over positive. F prime prime of negative 1, that's going to give me negative over positive. To determine the sign of the second derivative between 0 and root 3, I'll plug in 1. That gives me positive over positive. When I plug in 2, I get negative over positive. We have an interval of concave up, then concave down, then concave up, then concave down. Because our domain is all real numbers, f does exist at each of these possible points of inflection. And because the concavity changes at each of these possible points of inflection, they're no longer possible. They are points of inflection. To get the points of inflection, we need to find the y values. So when you plug in negative root 3, then we simplify. Our result is negative 3 root 3 over 2. We already know that f of 0 is 0. That's our intercept. And when you plug in root 3, you just get the positive version of when you plugged in negative root 3, which isn't always the case, but it is for this particular function. Our points of inflection are negative root 3, comma, negative 3 root 3 over 2, 0, 0, root 3, and positive 3 root 3 over 2. Let's graph. We have a point of inflection at negative root 3, comma, negative 3 root 3 over 2. Negative root 3 is approximately 1.7, and then negative 3 root 3 over 2 is about negative 2.6. Our other point of inflection is here. Let's check our intervals of concavity. Remember, from negative infinity to negative root 3, we are concave up. But then we look at f prime number line, and we're increasing. This entire graph is going to be increasing. Remember, there are no relative extrema. So increasing and concave up, increasing and concave down, increasing and concave up, and then increasing and concave down. There's our curve. In order to find the domain for example 2, we are going to need to factor this denominator, and if you notice, it's actually a perfect square trinomial that factors to be x minus 1 quantity squared. So our domain is all real numbers except positive 1, which would make that denominator equal to 0, and that makes positive 1 our vertical asymptote. Because this factor is to the power of 2, that means we have an even vertical asymptote, meaning the behavior on both sides will be the same. Holes are the things that reduce. The top does not factor and nothing reduces, so we have no holes. To find our x-intercepts, we make our function equal to 0, which is essentially making the numerator equal to 0. All right, add 2, divide 3, so x is 2/3. That is our x-intercept. And our y-intercept is when x is equal to 0, so if I plugged in 0, I would get negative 2 at the top and positive 1 at the bottom. So my y-intercept is negative 2. The degree of the numerator is 1. The degree of the denominator is 2. When the numerator degree is less than the denominator degree, then our end behavior is a horizontal asymptote at y equals 0. That means f of x will approach 0 no matter which direction we're headed, toward positive infinity or negative infinity when it comes to the x's. For relative extrema, we need to find the critical numbers. Critical numbers occur when our derivative is equal to 0 or when it's undefined. F prime of x is undefined at x equals 1, but that's already a domain restriction, a vertical asymptote, so it cannot be a critical number. Therefore, our critical numbers here will be when our derivative is equal to 0. And that's at x equals 1/3. Time to draw our f prime number line and determine our relative extrema. Make sure you put your critical number of 1/3 on here, but also indicate any domain restrictions, such as 1. I do like to put a vertical asymptote just to remind myself that cannot be a relative extrema because it's already a domain restriction. Now let's figure out the signs of our intervals. F prime of 0, which is to the left of 1/3, gives me a positive over a negative. This will be a negative interval where f prime is negative and therefore f is decreasing on that interval. F prime of 1/2 is between 1/3 and 1. 1/2 would give me a negative on the top and a negative on the bottom. So that's a positive interval. To the right of 1, let's just plug in 2 and see what is our sign. That's a negative on the top, but a positive on the bottom. So that is a negative interval on f prime, meaning f will be decreasing from 1 to infinity. Does our critical number represent a relative extrema? Yes, we're going from decreasing to increasing. So that is a relative minimum at x equals 1/3. And we'll need to plug that in to find the y value. No relative max on this graph, which puts the y value for our relative min at -9/4. For points of inflection, we look for where the second derivative is equal to 0 or where the second derivative is undefined. Here it's undefined at x equals 1, but we know that's already a vertical asymptote, so therefore cannot be a point of inflection. But where is it equal to 0? Wherever the numerator essentially is equal to 0. X equals 0, this is our only possible point of inflection. Let's test it out by making an f prime prime number line. We also put our domain restriction on the f prime prime number line and then check the intervals and their signs for concavity. The second derivative at -1 is a negative over a positive. Actually, this denominator will always be positive, so this is a negative result, this is positive, and this is positive. Our graph of f is concave down from -infinity to 0 and concave up from 0 to 1 and concave up from 1 to infinity. That means that our possible point of inflection at 0 is an actual point of inflection because the second derivative is equal to 0 at x equals 0 and the graph changes concavity. That point we already found the y value to. That's our y-intercept, and it's also a point of inflection. Time to graph. X equals 1 is an even vertical asymptote. 2/3 0 is an x-intercept. 0, -2 is a y-intercept and a point of inflection. 1/3 -9/4, that's -2 point something, is a relative minimum. Our end behavior asymptote is a horizontal one at y equals 0. And remember, that's determining end behavior, not behavior near the vertical asymptote. Now we have all the points that we need. Use the f prime and f prime prime number lines to help you connect the points and understand the curve of the graph. So first of all, from -infinity to 1/3, we are going to be decreasing, but we're only going to be concave down from -infinity to 0. So decreasing and concave down is my first part. Then in between 0 and 1/3 will be concave up, but still decreasing. In between 1/3 and 1, we are increasing and concave up. Because this is an even vertical asymptote, we know this side will also go up. It will have the same behavior. We know that from 1 to infinity, we are decreasing but concave up. And our horizontal asymptote guides us the rest of the way. For domain, a denominator cannot equal 0, and under a square root cannot be a negative. But it just so happens we have x squared plus 2. So yeah, nothing under this root is going to be negative, and actually nothing will make this equal to 0. So our domain is all real numbers from -infinity to infinity. We have no vertical asymptotes and no holes because we have no discontinuities. That's what an all real numbers domain looks like. Our x-intercept will occur where f of x is equal to 0, which basically means our numerator equals 0. All right, x equals 0 gives me an x-intercept. That means our x-intercept is 0, 0, which is also our y-intercept. To find end behavior, we're basically asking ourselves, what is the limit of f of x as x approaches negative infinity and as x approaches positive infinity? When determining limits as x approaches negative infinity or positive infinity, we only care about terms of highest degree in the numerator and the denominator. That would be the x in the numerator and the square root x squared in the denominator. We can simplify x over square root x squared to be x over absolute value x. X over absolute value x is a piecewise function. For all the x's greater than 0, the result is 1. For all the x's less than 0, the result is negative 1. So as your x's approach negative infinity, that would be x's less than 0, so this would result in a negative 1. And same as x approaches positive infinity, then that would be x is greater than 0, and our limit would equal 1. So our end behavior is f of x will approach negative 1 as the x's approach negative infinity, and f of x will approach positive 1 as the x's approach positive infinity. Relative extrema only occur at critical numbers. Critical numbers are where f prime of x is undefined or equal to 0. We already discussed how this denominator will never be 0, so all x's are available. And look at this numerator. That's never going to equal 0 either. So there are no critical numbers, meaning there are no relative extrema. We have no relative extrema, so our function is strictly monotonic. But is it monotonic increasing or is it monotonic decreasing? No matter what x value you plug in, your result for f prime will be positive, which means the graph of f is increasing. Possible points of inflection occur when the second derivative is undefined or equal to 0. Again, our denominator will not equal 0 here, so f prime prime of x is never undefined. But f prime prime of x will equal 0 when our numerator is equal to 0. That is at x equals 0. Is that a point of inflection? Let's make an f prime prime number line to check our concavity and determine if it's a point of inflection. When I plug in negative 1 and 1 to the second derivative to get this sign here, I get, remember the denominator is always going to be positive, so here our numerator is positive and the denominator is positive, and then here our numerator is negative and our denominator is positive. So we do have a point of inflection at 0. Our concavity is changing from concave up to concave down. And the point where this inflection occurs is 0, 0, our intercept. This gives me 1 point on the graph. And then our end behavior on this side is positive 1 and on this side is negative 1. But even though we only have 1 point, we have these number lines. F prime number line tells us that we are strictly increasing, and our F prime prime number line tells us about our concavity. So from negative infinity to 0, we are increasing but concave up. And I know we don't go below negative 1 because of my horizontal asymptote. Increasing and concave up. From 0 to positive infinity, we are still increasing, but this time concave down. And our boundary will be this horizontal asymptote.